All right, so I'm going to go back into my intro for Dave Holzer. As I mentioned, Dave has authored, more than 15 books, publications, and journal articles. And I just think that's amazing. Doing something like taking on writing a book is so much work and so much time. In addition to that, he has a live stream he's been doing about machine learning. And what I thought was so fun about this is I am a Python programmer, and he uses Python, and his name for this stream was also Dave's Python fails. So I can definitely relate to that. So without further ado, I am going to turn it over to Dave to talk about threat hunting, old data, new tricks.
Well, good morning. It is very nice to see everybody. I'm glad to be with you here. And as thank you very much for that introduction. I appreciate it. Yes, okay. So this is me. I know that I've met some of you. I know that some of you, someone was just telling me in my hallway channel that they've been looking at my face for the last month. So I really apologize about that. You get to see me again today. And I apologize, my background and everything isn't great today. I'm actually recording across the office today. I'm actually working through a recording for the on-demand version of a new class. I'll talk a little bit about that at the end. So this isn't like the ideal environment for this, but I want to talk to you a little bit about threat hunting, which is something that's near and dear to my heart, and it's something that I've really been engaged in for a very long time. And I'm sure that this is true of the other folks who are on the program here. I'm sure it's true of many of you who are tuned in too, depending on your age perhaps. But one of the things that I find is that we keep coming up with these new things, and and especially when you've been around for a while, you look at these new things and say, I don't know, is that new? Is that what you call the thing I've been doing for 15 years? Because we keep coming up with these new names. Yeah, just as one example, we went through this phase where we went through, micro segmentation and nano segmentation. We got to zero trust networking, the new thing. But most of us looked at that and said, isn't that defense in depth? I mean, that's what we've done forever. But we like to rebrand things and come up with new names. And of course, they're very important for marketing. But in terms of threat hunting and in terms of modern threat hunting, I want to talk about how things were done and how things are done today and how things probably should be done. Now, as I go through the presentation, please, you are welcome to go ahead and put questions into the question channel. That's actually pretty tough for me to keep track of because that just stacks right up. But I'll also be happy to answer questions live during the presentation too. So if I say something crazy, let me know. I do have my hallway channel open. I can kind of see that on the side here. But back when the internet dinosaurs roamed the earth, we had enterprises. So I was working in one enterprise, or how about this? A university would be better. I worked in a university in the early 1990s, late 1980s. We ran the entire university of 30,000 students off of one 1.5 megabit T1 line. I mean, the internet dinosaurs were roaming. The World Wide Web didn't exist. We used the WASE service, we used Gopher, we used Archie, things that are just long gone. Viruses were brand new, or really just a few years old, and there were still very well-known public figures using accounts with well-known accounts with no passwords. Like Richard Stallman, for many years, had an open account at MIT. And in those days, we paid for the time that we used on our systems, which was very painful. When it came to doing detection, which we didn't call threat hunting at the time, but it really was that. We were looking for anomalies that were occurring, bad things that were happening. And I am moving forward in time just a little bit. I'm now around the mid-1990s. The main way that we did threat hunting or anomaly detection at the time, it required a great deal of expertise. And we would collect all of the activities on the network, every single packet, and write filters to look at that traffic, dropping out everything we expected to see and only showing us the things that were left. Now, that does actually remain a useful way to find unknown behavior, but think about the scale of that. Because when you're running an enterprise over a 1.5 megabit line, you can manage that. But when you're running a network and you've got a 100 gigabit connection to the internet or bigger, there's no way you are manually going through that data. So the scale of things has definitely changed, even though threat hunting itself hasn't changed that much. Now I do see that for some reason I've lost control of the mouse. Oh, there we go. Okay. So what am I selling? I am selling absolutely nothing in terms of a product. I have nothing to give you that you should come and buy, and you're going to have this new tool that solves all your problems. And that's actually a big thing that I see happening in the industry. You're probably well aware of that. If you are a company who is selling some kind of cybersecurity product, or if you are running or working in a SOC or other network security team, when you talk to the vendors, every product they are selling, every product is going to have machine learning or AI, preferably AI, showing up. And threat, of course, we've got to work that in there too. Because today, if you want to sell a cybersecurity product, you had better be saying that it's an AI product, or no one's going to buy it. What's really interesting about that is thinking about what people in your organization believe that means. Now, I'm not going to ask you what you think it means, and I've got some experience doing this with cybersecurity people. Very frequently, cybersecurity people, whether they really know or they don't know, but they don't want to say that they don't know, they're going to say that, yeah, no, we get what that is. But you see, the people who are signing the checks, the people that the vendors are really marketing to, rarely understand what these terms really mean. I mean, I was talking to one cybersecurity vendor who's selling a host-based solution to do real-time anomaly detection to find things that are on your network affecting your systems using artificial intelligence and machine learning. And the product sounded amazing. And because I do research in this space, I'm very active doing stuff. And most of my work is dealing with network-based stuff. And I'm going to show you some of those things in a few minutes. They were doing system-based stuff. So I was really curious, how are you writing your classifiers? What are you using? And the first response was really a brush off. And I probed at that a bit more. And I finally got a response out of them. They explained, it's going to do this and it's going to run through. And then if it's unable to classify the activity, it's going to send it to the cloud for further analysis. So yeah, so like John is saying in my hallway right now, yeah, they're saying this is the silver bullet. This is going to make it no bad things can happen. And when they said that to me, I'm coming at this from a machine learning point of view, a data science point of view. So what I think is, and I ask, so what do you have? Are you paying for like massive GPU instances in the cloud where you aggregate all of the data and do additional training? And the person I was talking to, it was amazing. They get this baffled look on their face and they say, no, we send it to a human who decides whether it's good or bad. And then they update the rules. And when I heard that, I said, I feel like either I don't know what machine learning is, or you don't, or you are just choosing to lie in selling your product. Okay, so let's put that aside. We're going to look at some real applications of data science and machine learning to see if we can do some threat hunting. That's what we're interested in. And I'll apologize to you up front. I'm not going to go through the code to do it all. I'll explain it at a high level and show you some of the stuff. But if you've got specific questions, you can ask me. You're welcome to do that in the hallway afterward. I'm not going to do all the specifics now. And of course, there's a way you can learn how to do all that stuff. And I'll talk about that at the end. The thing, though, is that today, to do threat hunting with machine learning and AI, I don't think you really need to go buy stuff, at least not products like software. I think you can probably do it. All you need to do is know how to work with your data. And that's what this comes down to. We already have the data. Are we using the data effectively for threat hunting? Or do we have all the data and not know how to use it, so we have to go buy a product? Let me give you a few specific examples. If you are running an enterprise network, on your network you have enterprise class switches, routers, firewalls. almost certainly those devices already support NetFlow out of the box. Now, even if you've got Cisco products, which I'm really kind of not happy about, but it's the way it is, and Cisco products work well, their hardware is amazing, but they'll frequently add this in as an extra licensing cost, which kind of bugs me because they're the originators of NetFlow, even though it's an open standard today. You probably have this licensed. You might even be collecting the NetFlow data, which is metadata about every single network flow that occurs. You can think of that as a connection. I'm not going to be more specific than that. But if you're collecting it, are you using it? Now, in my experience, and admittedly, that's anecdotal. Now, I do work as the COO of a company. I'm the chief of operations for a managed security provider. But I also, because we're a managed security provider, engage with a lot of organizations. So this is anecdotal. I haven't gone and done a study on it, but my experience tells me that if you are using it, more than likely the only way you're using it is to generate some very simple dashboards. They will range from just health monitoring. Hey, the network's up. We can still see things are happening. And it's got a beautiful visual that's hanging on a wall in the NOC. But it could go all the way up to, we're generating some reports for things like unusual countries or which countries we're talking to, high bandwidth, overall usage, top talkers on our network. And those things are all wonderful. You should do those things. But to me, that's not really threatened. I mean, I might find something in there, but I think there's way more that we can do. So let's turn our attention, let's turn our skills, let's see if we can apply some data science to the problem of finding C2 channels and beacons, bots. And in particular, we're looking at reverse C2 channels. I'm not talking about someone who has established a long-term, it's up, that connection is always there. I'm looking for things that are engaged in periodic activity, beaconing. Now that beaconing could be that bot, but it could also just be, some other C2 channel. And I don't really care what protocol it is. See, that's one of the things. One of the issues that we've had when we go back in time, we look at how we did the anomaly detection originally, and it required a lot of expertise. And then when we tried to translate that to, I want to sell a product to you, what we did is we turned that expertise into signature detection. So for example, to find the signature for something, you'd be looking for maybe the protocol it's running on, and you're looking for a signature in the data. It's got this string in it. I know it's a backdoor. Or it's got, and we're not doing that here. I don't need a signature. I'm looking for a behavior. So what we're looking at here is a plot using the frequency or creating frequency, looking over time at the number of connections being established. I believe this chart is every minute on a connection over about a 48-hour period. And you can see that the network goes through, ups and downs. There's a long period of activity where there's a lot going on, probably during the day. But this is just everything that's happening. This is not an unusual way to look at things. I mean, this is probably what one of your health monitoring dashboards tells you. But how can I transform that into something I can do threat hunting with? Well, what I'm really interested in finding right now, I'm looking for beacons. I'm looking for this reverse C2. So that's going to be periodic activity, things that are happening regularly. There's actually a mathematics tool I can use for that. And if you're someone who's an electrical engineer or has engineering experience, you might be familiar with this. If I can get my slide to advance, there we go. Whoops, a little too far there. We can use a tool called Fourier transformations, a discrete Fourier transformation in particular. Now, you don't have to know all the math for this, but to explain briefly, this mathematician was doing research hundreds of years ago in an entirely different problem, and he discovered a really fascinating thing. He discovered that any periodic signal can be represented as a series expansion of the sine function. Now, we're not going to go through all that. I'm not going to show you the formula or anything. And that went down as sort of an interesting footnote that didn't really matter because nobody had anything to do with it. But then hundreds of years later, signaling becomes important and radio is invented. And then amongst other mathematicians. Claude Shannon does a phenomenal amount of work in signals analysis as the father of information theory. And, and we realize this Fourier transformation is actually really important. In fact, that's what you are looking at right now. Here, you are looking at a Fourier transformation of exactly that same data. And I hope you can see pretty clearly that around the middle, I'm going to tell you to ignore. There is a spike over on the left-hand side. I'm going to tell you to just ignore that. I'm going to just for now say it's related to a thing I'll call the DC offset, but I'm not going to explain it any more than that. But this signal right in the middle, there is clearly something that's going on. And what we've done using this transformation, which I see that there's a talk this afternoon about applying machine learning. And what I'm hearing is that they're going to talk a bit about this kind of thing. What this is doing is transforming from the time domain, which is how we looked at it at first. I could see connections over time. And we've now transformed that to the frequency domain. And I can see that there is a signal happening very regularly in this data. Now, there appears to be another signal over here on the right, and there very well might be, but there are some characteristics of this signal that tell me, based on my experience, that that looks much more like a harmonic of this main signal than some other signal. But I would investigate both. Here's the deal. Here's the point. We had all this data. It was all coming in NetFlow. It's already there. But is there a new way I can use it? Well, yeah. Why don't we transform it in this way and transform it into something I can actually use? And I see Robert Swigger, he's saying something, you could transform it back to the time domain. Yeah, you absolutely could do that. You can transform back to the time domain by figuring out what frequency that is. And in the particular sample size that I was using, the sampling frequency I was using, this works out to be about once every 20 minutes. This is occurring. Now, you may have already known about some of this. And I want to mention something because I have talked about this with some and they say, well, yeah, but for an attacker, it's very easy to defeat this. All you have to do is introduce a jitter, which means we're going to, not hit it every 20 minutes. We're going to go every 20 minutes, then maybe 18 minutes, then maybe 22 minutes. It's going to be a little wiggly. Well, yeah, that is a strategy, but I'll tell you that unless you make it random, I can account for that in doing my Fourier transformation and how I do my windowing and how I design my bins. So I will still find your signal. It really just depends how you go about it. But that's just one thing. Now, again, this is old data. This is something we already have. It's just applying a new technique. Let's look at another example of this. There's another great tool, another open source tool. There's a commercial version too, Corelight, but this open source tool called Zeek. I am a huge Zeek fan, and those of you who have taken 503 with me, you know that I love Zeek. I find that many people who are running Zeek are really missing out on what this tool can do. Because the way I see people using it, and to be fair, the commercial version of Zeek leads you in this direction. So if you're buying Zeek out of the box, you plug that thing in, you turn it on, and the first thing it asks you is, where's your SIM? And that's it. It's going to start shooting logs at your SIM. So many organizations are simply using this as a log generator into a SIM. Now, the tool can do way more than that. If you want to know what more it can do, you can have a look at the Zeek Slack. So the open source team runs a Zeek Slack. You can have a look in 503. We do a whole pile of stuff with this and create some really useful detection scripts across time and space within an organization. But even putting that aside, without writing any scripts, here again I have an old data source, something that's pushing into my SIM, that I can do some new stuff with. I can apply a new technique to it. Because rather than just letting those logs sit let that data sit in the log server, sit in the SIM, I want to know if there's ways that I can interact with that data. Are there things I can do with it? Now, one of the problems we have is that the data being generated can be very voluminous. So we're going to look at one particular log, the DNS log. The DNS log out of Zeek is going to have a record of every single query that has been made and the responses to it. That's a wonderfully useful log. But how do I use it? For our problem, I want you to imagine that you have a DNS log, or let's say in your SIM, you have a million DNS events that have occurred in maybe the last week, or maybe in the last day, or maybe in the last hour, depending how busy your network is or the scale of your network. How do I use that for finding threats? Well, maybe there's patterns that I should be looking for, patterns of queries or patterns of behavior, or maybe there are threats that I should be aware of. Well, that's what we're here for, threats, right? But the problem is that if I'm approaching this without machine learning, then probably the way we're approaching this is using a very old technique. And it's a technique we just keep using again and again. It's the thing we keep getting sold by vendors because it's very easy to implement. Maybe we're getting some threat intelligence information that gives us a list of known bad. If you see these domains, these are bad things. Or maybe I'm having a look to see if I've got really current common queries that are occurring. Maybe that's going to indicate there's something wrong. But there's a big problem with that. That's both simplistic. That would have worked 20 years ago. It's both simplistic, but additionally, how often will something like Google, or, if Google is against your politics, Bing or DuckDuckGo or whatever, how often will that appear? It's going to be in there so much, it's going to be really hard to get good statistics for anything else. Now, I'm not going to go about how to create good, robust statistics. I could teach you how to do that, but that's not what this presentation is for. These are very rudimentary methods. How could we apply data science to this? Well, in this case, the data science application we're going to look at is a machine learning application. In particular, we're looking at an unsupervised approach. This unsupervised approach, so my slides are out of control again. Let's try to go back. No, hold on. There we go. All right. So this unsupervised approach is being used to generate clusters for us. Now, unsupervised versus supervised learning in the machine learning space, there's a super basic way you can think about the two. With a supervised problem, I'm giving it training data to learn how to do things. And then I'm also giving it the answers to the problems I'm asking it to solve. So what it's really trying to do is finding a way to transform the data I give it as training data into the answers that I've provided. Now, for unsupervised learning, I'm giving it data to learn from, but I'm not telling it what that data means. I'm asking it to work it out for itself. Now, it would not be fair to give it, say, 1 million pictures and expect that it's going to come back and say, hey, that's a dog, because I haven't told it which things are dogs and which things are cats. But I could use an unsupervised system to give it 1 million pictures and have it come back and say, all right, these pictures are similar, and these pictures are similar, and these pictures are similar, and hopefully I've got dogs and cats and trees, or whatever else I've got in there. It just doesn't know how to label them. Well, that's called clustering. That's what we use unsupervised learning for. And the technique we're using here is a thing called DBScan, which sounds, when you first hear it, especially as an IT person, that sounds like database scanning of some kind, but it isn't. Databases are totally unrelated to this. This is distance-based spatial, I forget the A, I forget the whole rest of it, with noise. So it's clustering, distance-based spatial clustering with noise. It allows us to ignore the noise and create clusters. And it's a wonderful way to approach a problem like this. So what I've done is I've written some functions that will transform my DNS queries, those names, into numbers. That's actually one of the hurdles people often face with machine learning. In order to use it, everything has to be represented as numbers. So how do I do that? It's one of the big hurdles. Even when people go and take courses on how to do machine learning, they often leave unsure how to transform their problem into numbers. Well, I'm not going to go through the details of the functions I used, but I created a series of functions to add some dimensionality to this, to add some additional dimensions in terms of numbers representing these queries. That took about 15 minutes. And I then fed those million queries through that transformation function and did my clustering. And those million queries end up with a three-dimensional plot that looks like this. Now, to be fair, there were higher dimensions than this. There were more than 3 dimensions. So I did use some other mathematical trick on those features that I had engineered and used some principal component analysis to decompose it down to 3 dimensions. So we get this nice plot. And you can see there are clearly some clusters. In all, it comes up with 10 different clusters. And the question then becomes, what do those clusters mean? Oh, I'm sorry, I thought it was 9 different clusters. One of the things about this unsupervised learning, about this clustering, remember I talked about it in terms of giving it a million pictures. It can tell you these pictures cluster and these pictures cluster and these pictures cluster, but it can't tell you those are dogs. It's up to you to then look at them and see what they mean. Now, in the 9 clusters that were generated, there were some that were much more interesting than others. So all million queries are now down to 9 clusters. One of those clusters, a really strong cluster, was Google telemetry services that were coming back and forth, trying to figure out where you are and do geolocation, things like that. Another very strong source here, a cluster here, was ad-related services, ad-related telemetry, trying to learn about the browser and who the user is, things like that. There were also a really strong cluster for internal service lookups, which is, a huge thing in Active Directory. But one of the clusters revealed instantly that there was a C2 channel for an iodine covert channel running in the network now. Now that's a big deal. Here's just an example of one of those queries. There were several thousand of them, but one of those queries. And looking at that query, it's clearly unusual. I mean, this big long string of letters, and then you've got Microsoft, and it may not be apparent with the font I've used there, but that's Microsoft with a 0 for the O. That's pretty clearly anomalous. Now, we found that with clustering, and it's fair to look at that and say, but wait, couldn't we have used a known bad to identify that Microsoft string? Did I need machine learning for that? Well, no, you didn't. But it is trivial to reconfigure iodine to use some other domain, any domain you wanted to, really. But here's the thing. If you reconfigure that to some other random domain, it is no longer in any known bad list. Very easy to defeat the signature, which has long been the case with viruses, malware, with Trojans, with network attacks. Very easy to defeat signatures, but we keep on using them again and again. Still, if we change that to anything else and perform the same clustering, guess what? That iodine traffic instantly appears in a cluster. That's a pretty amazing thing, because what that does is it moves us away from requiring a known bad, requiring a signature, and being able to look for other bad things that are happening, to find the threats even when they are unknown threats. Still, it's not about the iodine. Instead, think about the scale of the problem. We had 1 million queries, and I'm asking you, find the anomalies in the 1 million queries. How do you do that? That's a huge problem to tackle. You could start removing things that you know are okay, but wow, that's a big problem. Looking at 1 million things is tough. What if I asked you to look at a small sample of a group of things out of only 9 clusters of data? That would be way easier. So someone is asking me, hey, would the iodine cluster be the same as the original, or would it be in a different cluster? We've run this several times, changing that domain name just to see how it behaves. It always appears as a cluster, but whether it's cluster 8 or cluster 4 or cluster 7, that's really kind of random. And that's not because we changed the domain name. That's because the dbScan process has some randomness thrown into it. So you would still have to go and track that thing down. But still, looking at 9 things compared to a million, and being able to take a million things and turn it into just 9 things to look at, that is a very manageable problem. There's other ways we can solve these problems, though. Other applications of data science and machine learning. So far, we've looked at one that just comes from signals analysis, Fourier transformation. The last one was unsupervised learning, doing clustering. But let's look at one that takes a look at deep learning neural networks, because honestly, when people hear about machine learning, that seems to be the thing people are most interested in. It feels the coolest, and you can get that to do amazing things. It really has been supplanting other approaches toward doing statistical learning. For example, I told you I'm recording a class this week. So the class I'm recording is the new SEC 595 course, which is the Applied Data Science and Machine Learning for Cybersecurity folks. And after wrapping up one of the sections, it was actually the section covering unsupervised learning and statistical modeling. One of the things covered there is random forests. I just recorded an extra piece for that, just showing how easy it is to even do image classification and handwriting recognition using a random forest. So if I can do such amazing things with a simple statistical technique, is there a need for these deep learning techniques? The answer is yes, because random forests have really reached their limit. There are problems that they just cannot solve. Using a very controlled data set, I can get it to do almost anything. But when I start dealing with an uncontrolled data set, so like what we're about to talk about here, let's say I want to find the answer to a more specific problem. I want to look for a more specific threat. I don't know exactly what that threat looks like, but here's what I'm thinking. It would be pretty useful to be able to find protocols, application protocols, that are running on weird ports. That would be kind of useful. That I would want to know what that is. There could be a threat there. Or I want to find unexpected protocols that are running on my network, things that I don't think I should have, but they're there. Which harkens back to what I said we were doing in the mid-90s, but has become very difficult to do at the scale we operate today. Or what if I find an unknown protocol? I have no idea what it is, and it's running on my network, maybe on a port that is a commonly used port. Is there a way for me to find those things? So let's turn our hand to this problem. And we're now looking at the results of using a deep learning neural network. And I'll be more specific. What's actually being used here is an autoencoder to do some anomaly detection. In fact, if this looks kind of interesting to you, I'm going to be talking a lot more about this tomorrow at a live stream. And I've got a link to that at the very end here. What you're looking at is, and I know the text is super hard to read, but what I was trying to show you is that this isn't just for one thing. Here we are looking at an autoencoder that has been trained to identify a whole variety of network protocols that might appear on my network. In this case here, it's showing me the difference between things that are that protocol. So if you look in each one of these graphs, you'll see that there's a blue line at the bottom. The blue line represents things that really are that. For instance, I can read in the top corner there, the top left, is the boot service discovery protocol. So in that boot service discovery protocol, the blue line, that's actual boot service discovery protocol packets going by. The orange line are things that are not that. The next one over is the DLNA service. The blue line is DLNA. The orange line are things that are not that, and so on for each protocol. And if you look at these, you'll notice that in every one of these, it would be trivial to draw a horizontal line right through that graph. And with that line, we are linearly separating things that are the right thing from things that aren't that thing. This is the result of a deep learning neural network using a specific technique called an autoencoder and measuring the loss, measuring the reconstruction loss. How well can it recreate this from the input data? the result is that it becomes simple to identify things that claim to be one thing but aren't that. This kind of technique is widely used for credit card fraud and other kinds of user activity with financial institutions, but I find that we are not using this kind of technique very widely in cybersecurity. Why not? Well, one reason is sometimes we just don't know how to, but the other one goes back to what I was saying before, and I saw some people typing about feature engineering. That is the big problem. I find that even when we have a great deal of domain expertise about how these technologies work, we don't know how to turn what we have into things that I can use with data science and these other kinds of approaches like machine learning. If we do it though, it turns out that building something like this, so building this network took, I think, from the time we had the idea to do it, to actually build it and train it, was something like 2 hours. Something like 2 hours. And this now is something that we run in real time, not only on our networks, but on customer networks to let us know when there's activity occurring that doesn't match the profile for that network. It's a protocol that we just have never seen, or it's running in a weird place, and it just lights up. And this is actually a bit different because there's other open source machine learning stuff for monitoring your network, like Poseidon and things like that. But the way those work, they require you to give it vast amounts of data up front, and usually has to run for months before you can start getting anything out of it. And worse, my big fear is when you use that kind of system where it's learning about how your network behaves to find anomalies, do any of you feel like maybe there could be things wrong on your network today? Even though you've bought every tool there is, you've got everything installed, you've followed all the best practices, you've got up-to-date signatures, you still feel like there could be something happening. I suspect you do feel that way, because if you didn't, you wouldn't be at a threat hunting seminar. I mean, that's what we're doing. We're finding those things that are the unknown attacks, the things that are unknown, the things that aren't lit up, the things that are not blocked. Well, if that's what I want to find, and I have a system that's going to learn by watching my network for 6 months, then in 6 months, it's going to believe that that existing threat is totally normal for me. And that's not useful for me. So I prefer things that can classify data and give me real-time results, which is what this does. If that's interesting to you, you might be interested in having a look at the live stream that we've been doing regularly. And it is true. So the official name is, what have I got here? I've got it somewhere. Applying Machine Learning to Network Anomalies. That's the official title of tomorrow's. It's down there at the bottom. I forget the official name of the live stream. It's bi-weekly, so we do it every 2 weeks. But it is, kind of subtitled Dave's Python Fails, because it's all live coded. So, expect things to not work sometimes. And we're coming up on our third broadcast tomorrow. Tomorrow's is actually a very interesting one because it's building on things that have already been done. Getting Zeek to send data out of Zeek to a Python listener, converting that data over into something we can actually use for machine learning. And then tomorrow at that live stream, what we're going to do is actually build an autoencoder, the thing I was just talking about, that we could then use in real time to begin getting data off our network and finding unusual activities. If that's interesting to you, maybe check out that live stream. And if you can't be there, they are recorded, because I know you're at a threat hunting summit, right? You've got other things to do perhaps this weekend. That's fine. Those things are recorded. You can go out to the Cyber Defense Blue Team channel. We've got those things archived there. They're also streamed across LinkedIn. But when you're listening to this keynote, I really do hope that you're getting another message. Think about everything that I talked about today, the things that I showed you. None of these things are using new data. They're taking the old data we already have, and we're just doing new things with them. And it's not so much that I'm applying new tools. I didn't go buy anything. I just used new techniques. I use new tricks, and we get new information out. If you want to learn more about this more generally, you want to be able to know how to use these tools effectively, you can absolutely take a look at the SEC 595 class. Now, I will tell you, I will, just like really every other science class, I mean, if you want to go put in the time and research and do it yourself, you can learn everything I'm telling you here by going and researching, taking a statistics course, taking an advanced mathematics course, going into deep learning. You can absolutely do that. Or SEC 595, we just boil it right all down for you. And you will leave with the tools you need to be able to do this stuff. Currently, the Orlando, so these are in quotes because, yeah, it's in Orlando by name, but it's a live stream. So it's not like I'm traveling to Orlando. I was really looking forward to it. It's going to be my first time out of the house in 2 years. But Orlando is sold out. Baltimore is not yet sold out, but is close. London is not yet sold out either. So if you're looking at doing this or interested in doing it, just have a look at those links. I do see one or two people who are asking me to post the links into the hallway. I will absolutely do that. But at this point, I just want to thank you so much for tuning in today. And I hope you got something out of this that was valuable, even if it was just making you curious about new ways to approach this problem. Thank you so very much.
David, thank you so much for a wonderful presentation and a great way to kick off the day. I think you were watching Slack and you answered quite a few of the questions that came in, but I caught a couple to maybe follow up with you on. One of them was from Dan that says, I have taken the 503, but for people who haven't, where do people go to learn Zeek? Does someone have a training course for it?
Well, that's an interesting question. So the Zeek team actually reached out to me a couple of years ago and asked me if I would write a course for them. And I was willing to do it, but the problem was they didn't really appreciate the scale of that. So I know that the Doug Burks team, I know that they do some stuff with Zeek and do a little training on it. But my understanding is that they don't really go further than we currently go in 503. There is some discussion about whether or not there could be enough interest to do kind of an advanced 503, like a 603 or something, or maybe merge that with the SOC operations. So there's currently nothing I know of beyond going and doing it yourself. However, if you take 503, and if you've taken 503, don't forget to stay in that Slack channel that we have. We have a Slack channel there that's been open for, I think, it's coming up on 5 years now. So if you're trying to solve a problem with Zeek and you don't know how to do it, go there because I will absolutely help you. You can also use the public Slack that the Zeek team maintains, and usually they're more than happy to help you out, but their answers may be less clear. I'll just say that. I mean, they're wonderful people, but they're busy doing other things. They just don't have time to write code for you. So I hope that's somewhat helpful. What other questions do we have?
Let's see. I have a question from Kevin. Will additional information be provided on the real-time automated anomaly detection? And then source code question mark.
Well, if you'd like to learn more about that specifically, then tune into the live stream that we're doing on the Blue Team channel. And I'm not going to give you, every scrap of source code related to it, but there is more than enough there for you to put the whole thing together and make it work. If you really want like finished source code related to that, there's a bit of it in 503 and there's a bunch of it in 595 because 595 is the machine learning class where we are building the stuff that makes that happen.
Excellent. Thank you so much.